Welcome to the video on Hartley oscillator. It is a one form of LC oscillator which uses two inductive reactances and one capacitive reactance, which was connected in the feedback network, is called as Hartley oscillator. So the frequency range of the Hartley oscillator between 20 kHz to 30 MHz. So please see the circuit diagram of the Hartley oscillator. So in this diagram, at first the amplifier stages uses an active device as a transistor in the common emitter configuration. Okay, so you are seeing the common emitter configuration of a transistor, and the resistance R1 and R2 are the biasing resistances, and here there is a RFC. RFC is called as radio frequency choke. Its reactance value is very high for high frequencies, and it can be treated as a open circuit. And for DC conditions, the reactance is 0, hence causes no problem for the DC capacitors. So that is what RFC function. And CC1, CC2 are called as the coupling capacitors, and here there is a RE is a emitter resistance, and CE is the emitter bypass capacitor which was connected. So, and in this side there is a tank circuit, right? The tank circuit which contains one capacitive component and two inductance component. So C is the capacitor and L1, L2 are the two inductor. So this circuit is called as tank circuit. The tank circuit can be also called as tuned circuit or resonating circuit. Now the first network is nothing but as common emitter amplifier, and the second network is nothing but as this tank circuit. So this common emitter amplifier provides a phase shift of 180 degree. As emitter is grounded, the base and the collector voltages are out of phase by 180 degree. As the center of L1 and L2 is grounded, when upper end becomes positive, the lower end becomes negative, and vice versa. So this LC feedback network gives an additional phase shift of 180 degree. So the total phase shift can be given as 360 degree, which is used to satisfy the oscillation conditions as per Barkasian criterion. So the whole circuit which produces 360 degree phase shift. Now next we can see the working of this Hartley oscillator. So in this circuit diagram, the output current, which is the collector current, that is what HFE into IB, okay, where IB is the base current, and we can assume that the coupling capacitors are short circuited. The capacitor C is between base and the collector. The inductance L1 is between base and emitter, while the inductance L2 is between collector and emitter. Now we are going to see the derivation of frequency of oscillations. Okay, now we are going to find out the frequency of oscillations F. Yes. Now the general equation for LC oscillator is given as HFE Z1 into Z2 plus Z3 into Z1 plus Z1 into Z2 plus HIE into Z1 plus Z2 plus Z3 equal to 0, where Z1 and Z2 are the inductors and Z3 is your capacitor. So here this HIE is nothing but as input impedance of the transistor, HFE is nothing but as hybrid forward gain of the amplifier. Now the first equation is the common equation for all kind of LC oscillator, and it is a very important equation. Now we are going to find out the frequency of oscillation. For finding the frequency of oscillation, we should set the imaginary part equal to 0. So before that, we should substitute the value of Z1, Z2 and Z3. So as I before told that Z1 and Z2 for inductors and Z3 is a capacitor. So the value of Z1 equal to j omega L1, Z2 equal to j omega L2, Z3 equal to j into omega C. So the j into omega, Z3 equal to 1 by j omega C. So that 1 by j omega C can be rewritten as minus j by omega C. Now I am going to substitute these three values like Z1, Z2 and Z3 in the first equation. So after substituting these three values, the equation can be minus HFE into omega square L1 into L2 plus L1 by C minus omega square L1 into L2 plus HIE j omega into L1 plus L2 minus 1 by omega square C equal to 0. Okay. So after substituting these three values, that is Z1, Z2 and Z3, these three values should be substituted in the first equation. We can get this equation as this one. So the first term and the second term and the third term, these three terms are called as the real part, and the fourth term is called as imaginary part. So let me take the imaginary part equal to 0. Okay. So HIE into j omega into L1 plus L2 minus of 1 by omega square C equal to 0. Okay. So now this HIE into j omega can be go to the RHS side. So these two terms can be considered as 0. Now L1 plus L2 minus 1 by omega square C equal to 0. Okay, now I am going to take minus 1 by omega square C in the right hand side, that is RHS. So L1 plus L2 equal to 1 by omega square C, where omega square equal to 1 by L1 plus L2 into C. So omega square equal to 1 by L1 plus L2 into C. So what is omega? Omega equal to 1 by root of L1 plus L2 into C. So the omega can be called as frequency of oscillation. So omega can be written as 2 pi f. Omega equal to 2 pi f. Now I am going to substitute the value 2 pi f here. So after substituting the value of 2 pi f, so then f equal to 1 by 2 pi root of L1 plus L2 into C. So this L1 plus L2 can be given as L equivalent. So the L equivalent is nothing but as equivalent of inductance is equal to L1 plus L2. So this red color equation is nothing but as the final frequency of oscillation of Hartley oscillator, f equal to 1 by 2 pi root of L equivalent into C. Now we are going to find out the condition oscillation. For condition oscillation, we should make the real part as 0. Okay, as I told before, the first three parts are called as real part. So here minus HFE omega square L1 L2 plus L1 by C minus omega square L1 L2 equal to 0. So all the real parts can be considered as 0. So by substituting the value of omega square in this equation, finally we can get the equation as L1 by C equal to L1 into L2 into 1 plus HFE divided by L1 plus L2 into C. So that is the final equation. So after that we can get the equation as L1 plus L2 by L2 equal to 1 by HFE. So finally the HFE, that is the forward gain, can be given as L1 by L2. This is called as condition of oscillation. And yes, this frequency expression is very important for Hartley oscillator. So the final expression f equal to 1 by 2 pi root of L equivalent into C. That is L equivalent equal to L1 plus L2. So both the inductors are connected in series. Okay, L equivalent equal to L1 plus L2. Now we can see the advantages of the Hartley oscillator. So the first point, here instead of using a large transformer, a single coil can be used as an auto transformer. That is the main advantage of Hartley oscillator. And the frequency can be varied by using a variable capacitor or variable inductor. So we can change the frequency as very easy. And the third one is less number of components are needed or sufficient for Hartley oscillator, and the circuit is very simple and easy to design. The last advantage, the amplitude of the output remains constant over a fixed frequency range. And let us see the drawbacks of the Hartley oscillator. It cannot be a low frequency oscillator, and the harmonic distortions may be present in the Hartley oscillator. And the applications are: it is used to produce a sine wave of desired frequency, and also it is used as a local oscillator in radio receivers, and also it can be used as RF oscillator. That is the applications of your Hartley oscillator. Thank you.